So driving CTE in fiber directions, we need to consider always constraint, which is that fiber directional strain is the always the same. So again, I like to restate the problem statement. We have a composite, matrix and fiber, alternatively like that. Each one has its own volume fraction. Now, this composite is exposed to a delta T, temperature increment. And now we like to know how much the strain will have. I mean, this is the epsilon x would be proportional to delta t, and with some coefficient alpha x. Alpha x is the coefficient of the thermal expansions in x directions. This is the definition. Now, the purpose of this is to calculate alpha x in terms of a fiber and resin property, okay? Now, let's take a look at the constitution, stress, strain, and temperature.
화면 공유 부탁드립니다. 교수님 화면 공유요.
Okay, thanks. So here, definition of the alpha x CTE in x direction is defined as the ratio between the x directional strain and delta T. Delta T is the temperature increment for this UD ply. Now let's take a look at each constituent. Fiber has the stress and strain and delta T, and resin matrix also has the stress and strain and delta T. So this is the stress strain temperature relations for each constituent, and as we already know, the fiber directional strain are all same. And so combining all of these, and we also have another relation is that sigma x, okay, sigma x is given as the fiber stress and matrix stress and volume fraction will be given as the sigma x. This we already know this equation. Now using these equations, sigma x will, fiber direction will go here. Sigma m will go to here, and then we also have this condition, and the strain in every direction will be the same. So this will go to here and go to here. Then as you can see, epsilon x comes from here. And we'll have this. And also there will be a term related to a temperature, and temperature delta T will be comes from here. So by definitions, besides this sigma x, there is no external stresses which will be given as a 0, right? And then delta t and from this and by definition of the CTE, there will be these terms. So this one will be given as here, and this term will go into here. And by the way, this is nothing but the stiffness. Well, you can say using the stress-strain relations and these terms as the considered as the what? This is the EX, right? So EX. Now we have to have this term and well, a little complicated, but this is the divided by the EX and something EX and delta T. Sorry, a little complicated, but here EX minus EX and these terms come to here, right? And then delta T. And by definition, this will be, we call alpha X. So alpha X is given like that. Okay. I mean, you don't have to fully follow the whole procedure, but the we need to understand the purpose of this derivation and the final result, and which is given in terms of a constitutive equation. As you can see here, we have a Poisson's CTE of a fiber, CTE of a matrix, and together with the Poisson's ratio, Young's modulus here, and fiber volume fraction. So this is the equations. This is the CTE in fiber direction. Now, how about the CTE in transverse direction? Again, let's define the problem statement. We have a matrix and fiber and matrix and fiber and so on. And there is no external stresses, no external stresses. That's the point. And then we just apply the delta T. When we derive the CTE in X direction, which we just got the result, that's how we get it. But another one, I mean, there will be another contraction or extension in Y direction. That is the given as the alpha Y, the CTE in transverse direction. And how do we calculate? Well, I will just follow the procedure. And this is the Poisson's rural mixture in Y direction. No matter how much the strain we have in Y direction, that is the rural mixture of the fiber and rural mixture of the matrix. And in terms of fiber volume fraction and matrix volume fraction. To come to this equation, again, I like to remind that we have a certain length, right? Certain length. And this will have a expand a certain amount, and this one will be a certain amount, and total strain will be like given like that. So Y directional strain is always following this one. Now here, and we need to keep in mind the constivication and fiber directional stress strain relations, and here is the given as a delta T, and this is the Poisson's ratio. Poisson's ratio given in terms of a stress. This is the fiber direction, and matrix direction. This is the CTE, and this is the Poisson's relations. Well, always in y direction, x direction, we have a same strain, and given as the alpha x delta t, which we just have it, and y we have, again, f direct, the fiber direction, we have constivications like that, and constivications is given like that. So when we have this term, okay, please pay attention. This one goes into here, and this one goes into here, and this one goes into here, and this one goes to here. So EY now is in terms of a delta T. Delta T is given here, and delta T is given here. And there are other terms. By the way, the fiber directions and extraction, they are all same. So these terms, we can say that we can use these terms and put it there. It takes a little, substitutions and so on. And now, finally, we would have the EY in y directional. We have a delta T, or in terms of a delta T. This is multiplied by delta T, and by definition of the CTE, we have EY and delta T. This is the definition of a CTE in y direction. So this is the CTE. Okay, so it takes a little derivations, but fundamentally, again, this is a Rurov mixture in y direction, and this is the fiber directional strain constraint, and fiber direction and matrix directions constivications. This is the equation we need to consider that, and we put them all into assemble, and we have a EY. EY and given like that. So I'd like to back to our Excel file. This is the x-directional y-directional CTE, and also this one is the x-directional CTE. Simply like that. Okay, so this one, to make the complete homogenized stiffness, we can add a CTE. I will call alpha x and CTE in Y. And for that purpose, we need to have of course, the CTE in fiber directions and CTE in Y directions, and the matrix direction. In fiber direction, the CTE, it could be differ in X direction and Y direction, but in this case, we assume to be the same. And so we have these terms. We have these terms. I would say alpha x like 10 to the minus 6. And resin, CTE is the higher. I would say about 20, 10 to the minus 6. So, and then alpha x is now given as a, just follow this equation, Poisson's ratio, BPF, oops, is equal, and alpha Poisson's ratio, and then multiply by EF times alpha x, alpha fiber plus Poisson's matrix fiber volume fraction times what? EM. EM is I need to change it a little bit here. I made a mistake, but I will do it later. And times what? Alpha M divided by, I need to look at this. I need to look at this equation. And then what? Divide by, well, you can use this one, but that is nothing but the EX, right? So divide by the EX. And that is the alpha X. Now alpha Y, we just derived, take some steps, but this is the final one, and equal to a volume fractions, VF, volume fraction VF times alpha extractions plus a VM times alpha M. Yeah, it is the a little complicated, but we need to follow VF times fiber volume fractions and the Poisson's ratio times alpha Y, alpha. It's always like that. Alpha F plus volume fractions times Poisson's ratio. Yeah, there is a misspell. This has to be a Poisson's effect, Vm, times alpha m, and divide by volume fractions times Poisson's ratio plus volume fractions times Poisson's ratio times finally alpha x. Alpha x is which we already have. Okay. Well, we didn't have a name yet, but let's call this one as the formula. Okay. Now this one has the sky is this one. Okay. Well, again, you know, it takes some derivation. It takes some steps to derive. You need to understand at least once, but as a final, you can just keep using this equation. And as you can see, fiber directional CTE is smaller than alpha x. And now I like to rearrange this one. I made a mistake here. I like to arrange this guy, go to here, and this guy go to here. It's better that way. This is the EM, this is the EFY, right? That's the one. Okay. We don't need this. So finally, we have all the material property for homogenize the properties like equivalent stiffness and Poisson's ratio and the CTE. Of course, these are dependent variables calculated from given this CTE of the fiber and resin. So when you calculate, when you perform any stress analysis using the micromechanical models or equations, you need to start from this property, fiber CTE and fiber stiffness, and same for the resin and so on. This is the quantification you have. And as a double check, this may not be exactly the same, but you need to, when we have a fiber volume fraction is equal 1, and then make sure that all the property has the same as the fiber, but pay attention to alpha y does not follow. There is some reason, but this is the usual trend. And also, if this is the 0, means that all the composite will become nothing but the matrix. And pay attention that all the property will be the same as the resin system, right? 3 point this and that same, and ES it will be the same. And this is the alpha x will be the same, but again, this one has some exceptions, which we will cover next time. Okay, so the this one is the also important important roles. When we have a very small amount of the fiber, very small amount of fiber, and pay attention to the final form and the stress amplification factors. So please understand what are the given. Well, given the fiber and matrix property, and the output will be a stress amplification factors and the homogenized material property. And this is the stress-strain relationship. And also you can say that here we need to have a strain versus temperature. And this is the alpha x. Alpha x will be given as here. And this one also are given as this one. Sorry, this one. Okay, sure, does not contribute to any thermal strain. So this is the full quantification for the composite. We will use these terms when we cover other subjects. Okay, when we cover the stiffness and temperature relation for the UD property, this is very useful relations, quantifications. And we gonna use these terms. But now I like to emphasize the how we're gonna do with these stress amplification factors. Okay, that is the one of the most important topic we need to cover. We need to fully understand in micromechanics. And the again, I like to summarize what we do. What we do is that this is the ply composite, okay? Again, I like to emphasize, you may not be able to follow all the equation and steps. You can just follow them in the class, but you don't have to fully, you cannot fully understand every time. But don't forget this overall flow. Don't forget this, the procedures of what we do. Basically, what we like to do is the composites. In composite level, we have a stresses subject to sigma x, or sometimes we call sigma x bar, okay, depending on the situation. And we have a epsilon x or epsilon bar. And here we have some, another stress is a sigma y and epsilon y. And we have a strain, shear strain as well. And the same for the resin. Here, 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 and there. Always these three component stresses, and fiber, same. Shear and the two tension stress. So stress strain temperature relations, we like to have epsilon x, epsilon y, and sigma epsilon s. And sigma x, sigma y, and sigma s minus alpha x and alpha y and 0 and delta t. That is the, this is gonna be 1 over x and so on. So this is the one we want to calculate, and this is the one we want to calculate from a given a constitution of a resin and constitution of a fiber. Now, another one is that, say, stress amplification factor for resin system, and given these ply level stresses, sigma x and sigma y and sigma s, this is the M matrix, and this will be a stress in the resin. So I would call sigma x matrix, sigma y matrix, and sigma s matrix, right? So this is the relations. And same for the fiber, sigma x fiber, sigma y fiber, sigma s fiber, and then this is the M matrix. So this will be a fiber, and this, this is the matrix, and this is the fiber. And same for the sigma x and y and s. This is the own axis. So given fiber direction, given UD steep stresses, and we want to calculate the ply level strain, same, given ply stress, you like to calculate the fiber or resin stresses using the stress amplification factor. Okay, this is the global view. I'm repeating the purpose of these sections. And this is the constitution, and this is the set, CTE. And this is the one we want to calculate. Of course, there is a term which I didn't emphasize here. We have, I mean, similar to a CTE, we could have I'm sorry, here we have a called AX, AY, and AS, and delta T, and for the fiber, and same here. So for the given, but we often neglect. There are some reasons why we able to neglect. So we may neglect this term, but this term and this term is important. Now, what is left is the subject regarding a strength. Okay, strength is the one we want to know. What it means that, say we have a resin system. Okay, resin has the strength is called yield strength. We have a yield strength. And fiber, okay, we also have a failure strength. Say fiber failure strength in extractions. So we often call fiber strength. Okay, fiber strength means that this fiber reach certain stress, it will fail. Very simple. And resin now is a combined stresses, all the stresses, and we calculate the yield strength like a Van Mises stress. So we need to have all these stresses and goes to here. This is the similar to a Van Mises process, and compare with the yield strength of the resin. And once you reach, the resin will become plastic. And fiber, once reach this fiber strength, that fiber will fail. So again, I'm repeating same stuff, but since it's so important, like to repeat again. Stress-strain relations, we have a stress and we calculate the composite strain, okay, using the quantifications. Now using these stresses, we can calculate a we calculate the how much stress in the matrix, how much stress in fiber directly. So using that one, we can tell whether resin fail or not. Also, we can tell whether fiber fail or not. Well, but in resin, mostly plastic behavior. In fiber, mostly like a brittle failure. So that is the how we define the ply strength. Okay, ply strength can be given as the resin failure or fiber failure. So that's the subject we would like to cover. This one, to understand this subject, of course, we need to understand a little bit about micromechanics, but we will back to this one in detail once we cover the proper chapters. But point is that longitudinal tensile strength, as I mentioned, we have a composite, and this is a subject to in fiber direction sigma x. Now, when it fails, this fail, we call this strength is the x. What is the x? Okay, x is the ply strength in fiber direction. Okay, x direction. We call large x. So what is the ply strength in x direction in terms of resin property, resin strength, in terms of the fiber strength? So back to the rural mixture in fiber direction, we always have these relations, and now the failure occurs. Okay, failure occur when the fiber fail. Fiber fail, it has the fiber strength. Now we do know that epsilon x is the same as the fiber and same as the matrix. And this fiber stiffness, I mean the strain, is simply defined as the stress divided by the Young's modulus. And same for the resin, stiffness is relating the stress and the strain. Okay, so so if we use this one, and when it fail, when the ply fail, so sigma x will reach certain strength which we want to drive, and then this a fiber directional strength and matrix directional the stress will be here. Look at this one. Okay, this is it comes from here. This one has sigma xm, it comes to here, but sigma xm is the Young's, we goes to here, and that is the one we have it like that, right? So sigma xm is like that. And also sigma xf, when it fails, it reach xf, and there's a volume fractions vf. So, but the point is that there is the xf here, because this is the also reach the xf. So as a final form, we have a this term, and xf, and this is the this term is very small. This is the how we get calculate the strength ply in terms of fiber strength. But similarly, since we already know sigma x, sigma fiber, and mf sigma x, we can directly say sigma f reach a fiber strength, then this xf will be a x, right? So x is simply, this will be m11 f divided by the xf, which is the xf, right? So this is the fiber strength, and this is the ply strength, simply divide by the m11f. What is the m11f? Well, let's get back to the equation we got for the m11f, and 111 here. Okay, so this is the one m11f is this one. So as you can see, the terms will be the same as this one, right? So you may drive equations like that using the full Rurov mixture, but alternatively, you can use stress amplification factor, and you can directly calculate the fiber stress, and this fiber stress will reach the fiber strength, and that is the moment when the ply fail. Okay, so this is how we calculate the sigma x, I mean the fiber directional strength. And also y directional failure. Remember, we have the sigma y fiber and sigma y matrix, and equal sigma y, right? So stress amplification factor is always the 1. But alternatively, this is not so much accurate, because in composite, the fiber is not the completely alternating. Instead, if we look at the fiber volume fractions like that, and that is the not the same as this kind of configuration. So when it subject to a transverse loading, this one is not completely same. As you can see here, this is the sigma y, and the fiber stress is somewhat changed, and matrix stress is somewhat changed. So that's the how we assume stress partitioning factor. So it means that, okay, fiber and matrix, there are some ratio called is experimentally say half 0.5. So previously we just assumed that sigma y equal sigma y, but in more accurately, it's better to introduce a stress partitioning factor, and using the rural mixture, then we can calculate the, I mean, here using this one and using that one, when we reach the fiber, I mean, this resin reach a certain amount of the, this is the yield strength of a resin, then this is a transverse strength. We can do the exactly same. I'm for the shear here, sigma s m and sigma s we call a stress partitioning factor for the shear directions. And previously we had this equal 1, right? And instead of that, we also have sigma s is the volume fractions of the m, and sigma sm, and plus vf and sigma sf. So using that one and using that one, that's the how we get these terms. So here I would say introducing stress amplification factor, I mean, factor can be enhanced using that similar to these procedures. We will get back to this equation, but since we don't have much time, we just go through the result. Another important point is that longitudinal compression strength, where the fiber, when subject to a composite, when it's subject to a compressive load, sigma x, when it is compressive, the fiber will easily fail, not material fail, but mostly relate to a fiber buckling or kinking procedures. So that is the quite depends on the Young's modulus of a matrix, because the fiber is supported by the Young's modulus of a resin system. There is some theory, and this is the how kind of equations. And same for the transverse compressible strength. Transverse compressible strength is the this and that. When this is subject to a sigma y, which is the negative, then the strength we call y prime, and y prime is also relate to a I mean, matrix dependent, and we often assume it's not exactly same, but the open can be much related to a resin strength. Okay, resin strength. Okay, so now we can upgrade these, update these terms, and the calculate the strengths. Strengths means that, as I mentioned here, here, as I mentioned, the strength of the composites can be given in terms of strength of a resin and strength of fiber, either through a micromechanics we just cover, or either through a stress amplification vectors. So X, okay, just a few more minutes, please. X is a strength. Okay, X is given, okay, given XF. What is XF? Well, XF it's not defined yet here, so we need to have some cells. And X is the strength, okay, fiber strength, and the XM is the matrix strength, which will usually, bond miss stress. Say this one, well, some arbitrary number, say, so let's say 1%, so 3 to 11, I mean 9, and this one 2%, so 5. 7. So let's just double check. Equal divide by this one, divide by the fiber. That is a failure strain 1%. And here this divide by resin. So about 1.5. This is the failure strain, fiber failure. This is the failure. Just to get the understand the meaning. Okay. So X is given as what? X is now 1 equal XF. XF is this one. Okay. Divide by the M11F is this one. Didn't assign the name yet. So this one, XF divided by we can do the same thing here. But X prime is a little different. It's not directly calculated from a stress partitioning factors. And this one is the somewhat relate to EM. EM is the what? EM is here, divided by the matrix volume fractions. And that's the one. And why? Why I would say a failure due to resin. So this is the call you can call here, as it says. And when the resin reach the failure, so similar to this, I'll just copy here. So instead of a fiber, I would call resin, and instead of this, I would call okay. I like to rearrange a little bit. This guy better to be here, and this guy is better to be here, and that here. I mean, we don't have to do it, but to be consistent. And right, so this one now for when fails, I mean, when the ply fails, when sigma y reach. So this one, instead of that, we use xm divided by x2 m, right? And shear is a shear is the same. We can see here is the same here. And instead of xm, we can say x, not just xm, but also we can have a xms, because the matrix can have its own shear failure, which we can define, okay? And this is the material property. So this one, this matrix and divide by what? This term. Now, but the compression is, as we examined, is a little different. Y prime, here EM, Y prime. Okay, Y prime is approximately same as the XM. Well, this theory is not complete, but I just like to have a complete sets of the parameters so that later you can update one by one. So here is the composite homogenized material property. And here is the stress amplification factors. And here is the strength in fiber and transverse direction and so on, right? And I'd like to share this equation, and then this is the, we roughly, okay, I'm sure there is some equation which you may not be able to follow. Well, just take it for granted, and we will come back again, okay? But I like to give you an overall picture of the micromechanics. What can we do with the micromechanics? That's the what we like to. I like to emphasize. Okay, don't worry about the detailed derivations. Just keep that in mind. What's the purpose of a micromechanics? Again, the purpose of a micromechanics is that given resin property and fiber property, stiffness and strength, the purpose of a micromechanics is to get the stiffness of the ply and strength of a ply. Okay, in doing so, we need to. It's better to define the stress amplification factor, which is very useful, directly calculate the stresses directly from ply stress. Okay. Okay, so that's the topic subject we would like to cover today. I'm sorry it's a little over 4 o'clock, but due to some problem in the network, this is one we like to today. Okay, so I'm sure you have some questions, but since the time is really almost 4:15, I'm sorry for that again. If you have any questions, please let us know, mainly through Katalog, okay? Okay, so this is the, now we need to close the class. Okay, so thank you so much. And then I'd like to share the Excel, and I also upload our class, and please go through and remind yourself of the purpose of micromechanics. Okay, thank you.